Okay, chapter 13, aldehydes and ketones. The common thing here is going to be a carbon-oxygen double bond. There's vanilla. All right? That's a natural product, and we won't dwell on this right now, but you can see this is something the vanilla plant makes, and it doesn't just hold itself to just one functional group. It's got a benzene ring, it's got a methoxy group over here, it's got an OH over here, it's got a carbon-oxygen double bond over there. So nature tends to be pretty creative about chemistry and is very, very good with chemistry. All right, here's an aldehyde. There's the condensed formula of it. It's not COH. If you see an COH, you think alcohol. You see CHO, you think aldehyde. Put the H first, and so that H is on that carbon. If we had RCOH, that H is on the oxygen. That H is on the carbon. And that oxygen is on the carbon. But how is it on the carbon? As a carbon-oxygen double bond. That's an aldehyde. All right? So aldehydes have the carbon-oxygen double bond on the end. It's always on the end. If it's not on the end, it's a ketone. The carbon-oxygen double bond is somewhere other than on the end, it's a ketone. All right, so here is a simple aldehyde, 3 carbons long. Propanol. We're taking the Al out of aldehyde and pulling it on in to the suffix. So you drop the E from propane and add Al, and you get propanol. Okay, so don't kind of slaughter your O's and L's and E's and A's in these names. Because if I can't tell what you have there, since you're not a doctor yet, and they can write any way they want to, I'd like to know you know what you're naming. So propane, propene, propanol, propanal, those are all different compounds, right? It's not just a minor spelling error, it's the wrong compound. So be careful with your spelling and make sure I can tell the difference between an A and an L and an O.
Excuse me.
Yeah.
What is the difference again between aldehyde and ketone?
Well, you can see it right here. This is on the end. The carbon-oxygen double bond is on the end. This carbon-oxygen double bond is in the middle. It's got a carbon on either side of it. So that's a ketone. And we're going to take the ONE and pull it in there, drop the E, and instead of propane, it's propanone. It's almost never called propanone. It's almost always called acetone. Those of you in the lab this morning, we're rinsing out your test tubes with acetone, that compound right there. It's a very, very common solvent in a laboratory in general, an organic laboratory in particular. All right, we'll maybe flash by this real quickly. There is a little bit of polarity. The carbon is somewhat positive, the oxygen is somewhat negative, but again, like the ethers, we don't have a hydrogen on here. There is some hydrogen bonding here, more so than ethers. Let's see if the next slide shows us that. Maybe the next one after this. So I'm going to draw a line right there. Let's look over here. Here is an aldehyde or a ketone, and it is showing the attraction of one, let's say, ketone molecule to another ketone molecule. You can see the oxygen in the carbon-oxygen double bond is going to be attracted to this carbon. because this has a slight positive, slight negative charge. And likewise, that oxygen is going to be attracted to the other the carbon on the other molecule. And you're getting some hydrogen or some dipole interactions right there. It's not hydrogen bonding, there's no hydrogen there. But there is an attraction. Dipole, because this is your dipole. This is a bond that has two poles on it, a negative, positive end. Like the Earth has the north and south pole. This has a positive and negative and positive pole. Here's the hydrogen bonding. Here's your ether or your ketone in water. And so the hydrogen on the water is attracted to the oxygen on the water is attracted to the carbon. Now that is hydrogen bonding. So let me just go back for a second. Right here. So let's see the impact of this attraction between molecules. All right? We just looked at this. Here's your nonpolar. We looked at this with ethers just a minute ago. Here is your alcohol. Oh, it's your alcohol, but it's your polar molecule. Here's your ether, mildly polar, just very little bit. Now remember, the boiling points, I'm going to round them off to 0, 100, 10. These boiling points right here. So let's just round these off to about 50. So the boiling point is an indicator of how strong the molecules are attracted to each other. All right? Higher the boiling point, the stronger the attraction. So two alcohol molecules have the strongest attraction in this series of molecules. The alkane has the least attraction to another alkane. The aldehydes and ketones are about halfway between these two. 50. So there's stronger attraction between molecules than ethers, but not as strong as an alcohol. Okay? That's what that should be telling you. So what would be kind of a summary statement? Molecules of similar molecular weights, the higher the boiling point, the higher the intermolecular attraction. Stronger the attraction the molecules have for one another. Which corresponds to more polar, the molecules, higher boiling points. All right, the more polar the molecules are, the higher the boiling points. Now remember, this is for molecules of similar molecular weight. All right, it wouldn't be fair to compare let's say hexanal, 6 carbons long, big molecule, to propanol. Right, that wouldn't be a fair comparison. Yeah, one's an alcohol, one's an aldehyde, but one is probably twice the molecular weight of the other one. Molecular weight, boiling point, generally speaking, as molecular weight increases, boiling point increases. if you had alcohols or aldehydes or ketones or anything, if everything else was the same, as the molecular weight went up, boiling point would go up. So when everything isn't the same, everything's changing, everything's different. This is an alkane, an ether, an alcohol, a aldehyde, a ketone. So now what we want to do is we want to keep this constant and then see what's happening to boiling point. And what we're saying is, so for molecules of similar molecular weight, the more polar they are, the higher the boiling point. Okay. Yeah, here's showing it right here. Here's molecular weight, here's boiling point. What do we got here? There's alkanes. So this is going to be like, I don't know what this is going to be. It should tell me how many carbons. This is probably going to be ethane and propane and butane and pentane and hexane. So alkanes. You increase the molecular weight of alkanes, boiling point goes up. Here are aldehydes and ketones. Increase the molecular weight, boiling point goes up. Just what I'm saying right there. Alcohols. Increase the molecular weight and the boiling point goes up. But now, what if I just slice right up through here? I go from an alkane, aldehyde and ketone, alcohol. Very similar molecular weights. But the alkane has always got a lower boiling point than the aldehyde and ketone, which always has a lower boiling point than the alcohol. All right? Try to absorb that graph. That's what that's saying. I can go over here, this molecular weight. Alkane, aldehyde. I don't know what that is. Oh, that's your key. Aldehyde and ketone, alcohol. Go over to this molecular weight. Alkane, aldehyde and ketone, alcohol. The alcohol is always beating out the aldehyde and ketone, which is always beating out the alkane in terms of boiling point, if you look at a particular molecular weight. Picture's worth 1,000 words. It's got a lot of data on it. Naming aldehydes. Okay. Now, since the aldehyde is always on the end, we don't need ones in front of them. It's always on the end. Methanol, ethanol, propanol. You can't have two propanol. You can't have this there because this has to be on the end. Butanol, hexanol. Okay? So you just take it. There'll be a slide here in a minute that will show you all the molecules these are some of them that you need to learn the two names. But there'll be a slide that I think has all of them on it. Okay, I'm going to fly right by this because this is pretty straightforward. All right, just drop the E, add Al, and you got the name of an aldehyde. Okay, now the ketones are a little bit different. Propanone. Now, there's only 3 carbons here, and that carbon-oxygen double bond can't be on the end. There's only one carbon that's not on the end, so it's propanone. Butanone. I don't need a number here either because there's butanone. And let me just draw underneath there. There's butanone. There's the other butanone. But you can see this would be 1,2 butanone. 1,2 butanone. There's no 3 butanone. The only butanone you can have is with the carbon-oxygen double bond on the second carbon. So the 2 is not necessary. All right, now just come on over here to octanone, 8 carbons long. This could be right here. It could be right there. It is right there on this molecule. So there is such a thing as a 2-octanone, a 3-octanone, a 4-octanone. Is there a 5-octanone? Why not? If I put it right there, I would start counting here. 1, 2, 3, 4. All right, so there isn't a 5, 6, 7 octanone. That would be another one of the, you'd call it a trick question. What is the correct name of 7-octanone? What's the correct name of 7-octanone? 2-octanone. Okay? If we put it right here, we would stop counting from this end. We would come over here, go 1, 2. So what is the correct name of 7-octanone? It's 2-octanone. Okay, yeah, we'll come back to this. Methyl ethyl ketone, acetone. Okay, go ahead and name that molecule. Are my slides giving you the names?
Oh yeah, this one does it actually.
Yeah, I guess this one does. All right. So it is an aldehyde. It's got 5 carbons long, so it is pentanal. Pentanal. That's the first thing you want to figure out is the parent name of the molecule. Although we're not going to call it 1-pentanal, wherever that aldehyde is carbon number 1. We start counting from that end. 1, 2, 3, 4. So we have 4-methyl pentanal. Okay? Okay, here is 1, 2, 3, 4, 5. Yeah, no, this is not pentanal, this is pentanone. And we're going to start counting from the end that gets us to the carbon-oxygen double bond the quickest. All right, not a substituent. Why? Because we have actually included the carbon-oxygen double bond is what's driving the parent name. Pentanone. So it's going to be 2-pentanone. It's going to be 2-pentanone. And it's 4-chloro 2-pentanone. Okay, you can see the groundwork we laid in chapter 10. You know, it's making these things are. We have to learn a little nuance. What do we call ketones? We call them this pentanones. Pentanone. All right, here's the slide you should pay attention to. In terms of 3x5 cards, you should know that methanal is also called formaldehyde. Now you know what formaldehyde is. So single carbon aldehyde. Formaldehyde. Ethanal is most often called acetaldehyde. Acetaldehyde. A-C-E-T. And then aldehyde. Propanal is called propionaldehyde. Butanil is, what, are you going to have to learn all of these? Maybe. Butanil is butyraldehyde. Butyr. Okay, that you should, butanil, B-U-T. The common name is butyr. B-U-T-Y-R. Butyraldehyde. Then benzaldehyde, there you got like benzene with an aldehyde on it. Now keep in mind that what that looks like is this. There's your benzene, and then you have another carbon attached to it, and you have this aldehyde group. So that aldehyde group is not in the ring. It's attached outside the ring. And then, of course, there's a hydrogen on each of these carbons. That's benzaldehyde. Okay, let me pause there for a second. When you are drawing these, like benzene or toluene, you're drawing either a line formula or a structural formula. Don't get the two mixed up. Sometimes what people do is they come along here and they'll draw this and they'll put these carbons here. Don't do this, okay? You may have done it on one of your homeworks and I didn't count it off, but that gets a little bit confusing because I have a hard time telling whether you mean there's a carbon in that ring or you're talking about a carbon that's outside the ring. Okay, that gets confusing. So if you're doing a structural formula, put the carbons right in line. They got bonds going to them. You see how I do it. If you want to do a line formula, do a line formula, and then if you want to attach something to it, draw a line to it. Whether it be a CH, here, let's put a ring in there. Whether it be a CH3 or an OH or something. But this here gets confusing. This is got a question mark over it. I don't know whether that C is the one you think's in the ring or something attached outside the ring. Okay, 3x5 cards. All right, this is so common. Acetone is the common name of propanone. So you need to learn that molecule. Yeah, you can skip the bottom one. This next to the last one, butanone. Look at that. This is methyl ethyl ketone. It's a ketone. And someone might jump in there and say, boy, don't they have that in the wrong order alphabetically? Yes. Is that what we call it? Yes. Okay. So we call it methyl ethyl ketone, or you can go into a lab and find a bottle labeled with MEK. You say, is that somebody's initials? No, that's methyl ethyl ketone. Now, if someone works in the lab with the initials MEK, then we got a problem. Because we're going to think every bottle is methyl ethyl ketone. So that one actually has three names: butanone, methyl ethyl ketone, or it's distilled down to, or simplified down to MEK. Sorry about that. There's 7 more 3x5 cards. Every chapter has 5, 6, 7. Okay, you don't need to learn this. I want you to be aware of it. You've heard of omega-3 fatty acids, right? Omega-3 fatty acids. Well, they're using the Greek letter omega. The Greek alphabet starts with the letter alpha and it ends with the letter omega. So So even the terminology omega-3 fatty acids is coming off of this system right here, where you're using Greek letters to, so this is your aldehyde. What is the alpha carbon? This is the alpha carbon attached to that aldehyde. The beta, gamma, delta. What we're doing is going down through the Greek alphabet. Alpha, beta, gamma, delta. And so omega-3 fatty acids are not necessarily that they go through the whole alphabet. They're saying that's alpha, that's one end, omega is on the other end. It isn't necessarily gone through the whole Greek alphabet. It's just saying the other end, the other end of the molecule. This is the alpha end, and then there's an omega. And we'll get to omega-3 fatty acids, but they have an acid, and then they go down here, and this would be your omega. This would be your alpha position right here. This is your carbon. It's right next to the carboxylic acid. This is the last carbon. And omega-3 fatty acids are polyunsaturated fatty acids. They have double bonds. And this is wrong because these are trans. They'd be cis double bonds. So I'm not going to redraw it. They'd all be cis bonds, but that's what omega-3 fatty acids are. They're going off of this. And why should you be aware of this? You might be reading a paper or reading the name of a drug, and it says it's beta hydroxy something or other. You go, I wonder what that is. It means there's a hydroxyl group on the beta carbon in this molecule. This is not IUPAC. This is a traditional naming, common names of aldehydes. So Valero Corporation is coming off of this, valeraldehyde. So 1, 2, 3, 4, 5 carbons long. That is a common name. So just for awareness. Okay, some real common ketones. We talked butanone. This is butanone, methylethyl ketone, or MEK. Let's write down under here that this is also butanone. That would be its IUPAC name. Acetone, dimethyl ketone, or propanone. It's almost always called acetone. Okay. Again, 5 minutes. Name these aldehydes and ketones.